Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Quickly let me know in the chats, every one of you. Quickly, my dear students. I might cough in between, okay? I hope that is manageable. So quickly in the chats, if all of you can hear me, if audio video is perfectly clear. Guys, I'm better than before, thank you. All right. So just let me know in the chats like how many of you are done with the first session of your general organic chemistry, in which I discussed the complete IUPAC nomenclature in one shot. Just let me know that in the chat. How many of you are done with that? Just say yes or no in the chats. Yes or no, yes or no. The first session which I took for GOC, that was your IUPAC nomenclature, right? That was complete in one session, which was almost for 3 hours. Just let me know in the chats, how many of you watched that? Well, I believe majority of the students have watched that already. That's great, wonderful. And I would want you guys to make the notes as well. Okay, I hope you are doing that too. I hope you guys are making the notes too, guys. Okay? And today's session is going to be super important. Okay, because today we shall be discussing something really amazing, guys. Right? Almost some 100 questions we'll be doing in the today's session. Yeah? Isn't that amazing? So, let's get going then. Let's get started. But before starting the session, the ones who have not liked the session yet, I would want every one of you to like the session right now. Yes? I can see everyone has not liked the session, and I would want every one of you to like the session. Share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for every single one, right? Let everyone get benefited out of these sessions which we take on this particular channel, people, right? And at the same time, the ones who have not subscribed the channel yet, I would want every one of you to subscribe to your Unacademy NEET English as well. Okay? Perfecto. Duration of the session will be almost 2.5 hours, something like that. 2.5 hours. Yeah? So I would want you guys to be with me till the end. All right then. So let's get going. Let's get started with the term which is mentioned here. Charged species and their stability. Charged species and their stability. My dear students, if you first of all ask me, what is a charged species? This is something which I believe every one of you would be knowing. What is a charged species? I'll say any atom or group of atoms. Any atom or group of atoms having charge on it. Having charge on it is something which you call as charged species. Whenever you see an atom carrying certain charge or group of atoms carrying certain charge, right? The charge can be positive as well as negative. Any atom or group of atoms having any sort of charge on it, that is something which you call as a charged species, right? And my dear students, for the charged species, we are going to define a term. We are going to define a new term for the charged species. And what is that new term? That new term is what you call as volume charge density. So first of all, this volume charge density, which you are going to represent with VCD from now onwards, it is defined for all the charged species, right? First thing, any atom or group of atoms having any sort of charge on it is something which you call as the charged species. Now, my dear students, for a particular charged species, we are going to define a term which is VCD, basically, volume charge density. Now, you must be thinking what this volume charge density is all about. It is a very simple and basic term, guys. Volume charge density is simply the ratio of, charge on the species to that of size of the species. It is simply defined as the ratio of charge on the species to that of size of the species. As simple as that. Okay? Now we will try to understand what exactly I'm going to say. For example, imagine that I have got two species like this. This is species number 1 and this is species number 2. The charge present on this particular species is negative. The charge present on this particular species is negative. I'm assuming the two charged species which I've taken over here, I'm assuming the magnitude of charge present on both is same. Perfect. So over here, for these two particular species, which volume charge density am I going to define? Am I going to define positive volume charge density or negative volume charge density? I'm absolutely going to define the negative volume charge density. I'm assuming the two species which I have over here, they have got same magnitude of negative charge over them. Now, my dear students, if I ask you, among these two species, which particular species has got more negative volume charge density? Which species among these two has got more negative volume charge density? Have a look. So it is simple. The charge present on both is same. The magnitude of charge is same. So you are not going to decide on the basis of charge. You will be deciding on the basis of size. I would say this particular species, it has got lesser size, right? Lesser size means more volume charge density. So I would say the negative volume charge density of the first species will be more than that of second. As simple as that. Okay? Lesser the size, more the volume charge density. Perfect. For example, you have got two species like this. Guys, this is something very important. You will understand its significance in some time. Okay? Let's say this is one species which I have, and this is one bigger size species, right? I'm assuming these are both positively charged species. Now, for these two species, which volume charge density am I going to define? I'm going to define the positive volume charge density for both these species. Now, if I ask you simply, among these two positively charged species, which species has got more positive volume charge density? Have a look. The magnitude of positive charge is same. It is just the difference lies in size. Lesser the size, more the volume charge density. Lesser the size, more the volume charge density. So I would say the more positive volume charge density will be for first as that of the second. I believe this particular term is clear. Right? Okay. So my dear students, try to understand exactly what I'm going to say. First of all, I defined a charged species. Any atom or group of atoms having any sort of charge on it is what you call a charged species. And for the charged species, we define a term that's called as volume charge density. Volume charge density is simply the ratio of charge present on the species to that of size of the species. Perfect. This volume charge density can be of two types. One is going to be the positive volume charge density, which is defined for the positively charged species. The second one is going to be negative volume charge density, which is defined basically for what? Which is defined for the negatively charged species. Okay, as simple as that. Perfect. Now we will one more thing. This volume charge density which we have defined over here, it is related to stability basically. It is related to stability. Do remember this particular statement as well. Stability, it is basically inversely proportional to volume charge density. This is something very, very, very important. It is significance. you are going to get in some time. You are going to get this, the significance of this particular result in some time, people. Stability of the charged species is inversely proportional to volume charge density. It is inversely proportional to volume charge density. More the volume charge density of a particular species, right? I'm writing it over here. More the volume charge density of a particular species, I would say more is going to be its potential energy. More potential energy, more energy, which itself tells you that stability is going to be less. That stability is going to be less, right? Stability is going to be less. For example, have a look. I have got oxygen carrying the negative charge. I have got sulfur carrying the negative charge. If I ask you, among these two species, where is the negative charge more stable? If I ask you, among these two species, where is the negative charge more stable? My dear students, what exactly you are going to do is have a look first of all. This is negatively charged, this is negatively charged, right? If I ask you, among these two species, which one has got lesser volume charge density? Because the lesser the volume charge density, more is going to be the stability, right? Now you already know volume charge density is inversely proportional to size. The charge on both is same, right? Now look at the size. Sulfur has got more size than that of oxygen. If sulfur has got more size, its volume charge density will be less. And lesser the volume charge density means more is going to be the stability. So I would say negative charge on sulfur will be more stable than that of negative charge on oxygen. Correct? I believe these three terminologies are absolutely clear to you. Right? Volume charge density is defined for the charged species, which is always equal to charge on the species divided by size of the species. Volume charge density is inversely proportional to stability as well. Whenever you see a charged species whose VCD is more VCD means more potential energy. More potential energy means lesser the stability. Okay? Lesser the stability. I hope this is clear to everyone. Just try to understand one by one what exactly I'm talking about. My dear students, this is all basics which I'm telling you, and you will be using all these basics in some time, in just half an hour. But first, I need to cover up all the basic things which are required. Okay? There is something which every one of you would have heard. That is electronegativity. Can you define the term electronegativity for me? How do you define the term electronegativity? My dear students, there are many ways to define electronegativity. How exactly? First thing, electronegativity. How do we exactly define it? Electronegativity, it gives me the tendency of the atom of an element to attract the bonded pair of electron towards itself. Let me write its definition first. The tendency of an atom of an element. The tendency of an atom of an element. Attract the bonded pair. Or you can say shared pair towards itself. Now try to understand what it means. See guys, I have to basically tell you few things about it, which I'll be using frequently in this chapter. For example, I have got a covalent bond between A and B. Let's say I've got a covalent bond between A and B. I'm assuming that B is more electronegative than A. Now, my dear students, instead of this dash, I'll be showing the bond pair over here. Since there's a covalent bond between A and B, right? So it has to be the mutual sharing of electrons here. Absolutely. Now I'm assuming that B is more electronegative than A. What does that mean? That means B has got more tendency. It has got more tendency to attract the bonded pair towards itself. So I would say, due to the electronegativity difference between A and B, the bonded pair won't be exactly at the center. It would have got shifted towards B. it would have got shifted towards B, due to which electron density towards B would have increased and electron density towards A would have decreased. And the increase in the electron density towards B is represented by delta negative, and decrease in the decrease in the electron density towards A is represented by delta positive. Correct? Delta positive. As simple as that. Now, people, for example, there is a double bond between A and B. Assume that there is a double bond between A and B. At the same time, I'm assuming B is more electronegative than A. That means B has got more tendency to attract the bonded pairs towards itself. So, what would have happened? The electron density towards B would have increased. And that increase in the electron density towards B, I'll be representing that with -2 delta. And decrease in the electron density towards A, I'll be representing that with +2 delta. As simple as that. Now, my dear students, imagine there's a triple bond between A and B, right? B is more electronegative. So all the 3 bond pairs towards B, due to which it will get -3 delta. This will get +3 delta. So if I ask you now what electronegativity is all about, it is basically the tendency of the atom of an element. The tendency of the atom of an element to attract the bonded pair of electron towards itself. To attract the bonded pair of electron towards itself. So more the electronegativity of an element, more is its tendency to attract the bonded pair of electron towards itself. Number 1. Number 2. What kind of information this electronegativity gives us about the atom? What kind of information this electronegativity gives us about the atom of an element? What kind of information? There are a few points which you need to know. My dear students, this particular electronegativity concept, let me tell you, it gives the tendency, of an element, or I'll write of an atom of an element. It gives the tendency of the atom of an element to hold its valence electrons. What does that mean? That means more the electronegativity of an element, more is going to be its tendency to hold its valence electrons. I hope you're getting it. More electronegative element is going to hold its valence electrons firmly towards itself. This is something which we are going to frequently use. More electronegative element has got more tendency to hold its valence electrons towards itself. So, I can say it like this. If you want to take the outermost electron out in case of more electronegative element, is it going to be easy or difficult? It is going to be difficult. In simpler words. Okay? So, the concept of electronegativity, it gives me the tendency of the atom of an element to hold its valence electrons. More electronegative element is going to firmly hold its valence electrons towards itself. Right? As simple as that. My dear students, this concept of electronegativity, it gives us the idea about some more things as well. My dear students, it gives the tendency of an atom of an element. Or let me write it like this. It gives the idea about the negative charge carrying capacity. It gives the idea about the negative charge carrying capacity of an element. What does that mean? It gives the idea about the negative charge carrying capacity of the element. More electronegative the element, more is its tendency to hold the negative charge on it. Okay? It gives the idea about the negative charge carrying capacity of the element. more electronegative element has got more tendency, it has got more negative charge holding capacity. What does that mean? For example, I've got carbon carrying negative. I've got oxygen carrying negative. If I ask you where is the negative charge more stable? If I ask you where is the negative charge more stable? Oxygen is more electronegative than that of carbon. Oxygen is more electronegative than that of carbon. The concept of electronegativity, it gives me the idea about the negative charge carrying capacity. More electronegative element has got more negative charge carrying capacity. So among these two, which one has got more negative charge carrying capacity? Oxygen. It can sustain negative charge. It can sustain negative charge better than that of carbon. It can sustain negative charge better than that of carbon. You can understand it like this. Do remember, the negative charge carrying capacity of one oxygen atom, the negative charge carrying capacity of one oxygen atom is greater than the negative charge carrying capacity of 10 carbon atoms, my dear students. Now you can imagine. See, first thing we know, negative charge is more stable in oxygen, right? Okay. Negative charge is more stable in oxygen because more electronegative element has got more tendency, it has got more negative charge carrying capacity, right? And you can imagine it like this. The negative charge carrying capacity of one oxygen atom is greater than the negative charge carrying capacity of almost 10 carbon atoms. You can understand the difference. So let's not talk about this right now in detail. In some time, we'll talk about this a bit more in detail. But right now, I would want you guys to remember these points. Electronegativity, first of all, it gives me the tendency of the atom of the element, the bonded pair towards itself. It gives me the tendency of the atom of an element to hold its valence electrons. More electronegative element is going to hold its valence electrons firmly towards it. It gives me the idea about the negative charge carrying capacity of an element. More electronegative element will have more negative charge carrying capacity. As simple as that. Okay. Let me know in the chats if this is clear. Quickly. Let me know, my dear students, in the chats if it is clear. Quickly, people. Yes? Perfect. Now, people, few more things. Electronegativity, I'm sure you must have studied in your periodic classification as well. Electronegativity is inversely proportional to size. It is inversely proportional to size. You know it, right? So, when we move from left to the right in the periodic table, left to right, what happens to size generally? Size decreases. On moving from left to right in the periodic table, size generally decreases. And if size decreases, that automatically tells you electronegativity increases because both are inversely proportional, right? Similarly, when you move from top to the bottom, what happens to size? Size increases. And if size increases, what happens to electronegativity? Electronegativity decreases, right? One more simple thing which you must know. On moving from left to right in the periodic table, size decreases, electronegativity increases. Top to bottom, size increases, electronegativity decreases. And my dear students, the best part is, which you must know, electronegativity of orbitals is also defined. We define electronegativity for orbitals as well. Okay? And your s orbital, right? Since it is, if this is the nucleus, calling this s, calling this p, calling this d, calling this f. S is more close to the nucleus, and that is the reason why we consider the electronegativity of s orbital to be maximum. Electronegativity of orbitals is also defined, and electronegativity of s orbital will be more than that of p, will be more than that of d, will be more than that of f. One more important point which you have to remember, my dear students. Right? Okay? Perfect. This is one more thing which I would want you guys to know. Now we will few more basic things. If I particularly talk about carbon, if I ask you which kind of hybridization carbon shows, you'll say carbon always shows spi hybridization, right? Spi hybridization. And the value of I can be either 1, or it can be 2, or it can be 3. So carbon basically shows how many types of hybridizations? Carbon basically shows 3 types of hybridizations. Sp, sp2, sp3, sp3, right? Carbon basically shows three types of hybridization: sp, sp2, sp3. Now, what exactly I'm trying to convey here? You can understand. If I talk about the outermost configuration of carbon, it is 2s2, 2p2, 2s2 and 2p2, correct? 2s2, 2p2. Now, this is your s orbital, and this p subshell, it has got three orbitals. It's got three orbitals, right? This is your, imagine this is 2s orbital, this is 2px, this is 2py, for example, this is 2pz, okay? Now, my dear students, if the carbon shows sp hybridization, what does that mean? That means the s orbital and one of the p orbitals, one of the s orbital and one of the p orbitals of carbon, they have participated in the intermixing. They have participated in the intermixing, and you must be knowing number of atomic orbitals intermixing is equal to the number of hybrid orbitals formed. In case of sp hybridization, this s orbital and, for example, this p orbital, they'll intermix. Two orbitals are intermixing. They lead to the formation of two hybrid orbitals. And those two hybrid orbitals will arrange themselves in such a way that there should be minimum repulsions between them, right? So this is one of the sp hybrid orbital. This is one more sp hybrid orbital. If I ask you, when carbon undergoes sp hybridization, what is the bond angle over here? You will say directly it is 180 degree. Agreed? If I talk about sp2 hybridization, when carbon undergoes sp2 hybridization, what does that mean? That means one of the s orbitals of carbon and two p orbitals, one s, and out of these three, two p orbitals, they'll participate in the intermixing. So in total, how many orbitals are participating in intermixing? Three orbitals. Number of atomic orbitals participating in intermixing is equal to the number of hybrid orbitals formed. So how many hybrid orbitals will get formed here? I would say, since three atomic orbitals are participating in the intermixing, so three hybrid orbitals will get formed, right? Now these three hybrid orbitals, this is one of the hybrid orbitals. Similarly, there are total three hybrid orbitals. Now these three hybrid orbitals, they'll arrange themselves in such a way that there should be minimum repulsions between them, correct? Now, if I ask you, what is the angle between these hybrid orbitals over here? You'll say the angle between these hybrid orbitals right here, it is 120 degree. You must be knowing about that. In case of sp2 hybridization, the bond angle is 120, correct? Now people, try to understand. In case of sp3 hybridization, the s orbital and all the 3p orbitals, this s and all these 3p orbitals, they'll participate in the intermixing. So in total, 4 atomic orbitals are participating. And how many hybrid orbitals will be generated? Number of atomic orbitals participated is equal to the number of hybrid orbitals formed. So 4 hybrid orbitals will be formed. And those hybrid orbitals, they'll arrange themselves in such a way that there should be minimum repulsions between them, like this, which you all must be knowing. Your tetrahedral geometry, right? Most have studied as well. And what is the bond angle over here in this particular case? It is 109 degree 28 minutes. If I ask you what is the angle between these hybrid orbitals here, 109 degree 28 minutes, right? Perfect. I believe this is clear to everyone. Now, this was point number 1. Point number 2. My dear students, in case of one of the sp, this is sp hybrid orbital, this is one more sp. Similarly, this is one of the sp2 hybrid orbitals. Similarly, this is one of the sp3 hybrid orbitals. If I ask you, in case of sp orbital, in case of sp hybrid orbital, see how this sp hybrid orbital has got formed. It is basically one of the s orbital and one of the p orbital. They have intermixed and they have led to the formation of new orbital, which is sp hybrid orbital basically. Can I say in sp hybrid orbital there will be some s character involved, there will be some p character involved, because it's a hybrid. It's a hybrid of s and p, right? There will be some of the s character, there will be some of the p character involved. If I ask you, what is the percentage of s character in sp hybrid orbital? Percentage s character in sp hybrid orbital. Tell me, how many s orbitals have participated in this intermixing? 1 divided by how many total orbitals have intermixed? 2 multiplied by 100. So you'll say percentage s character in case of sp hybrid orbital is 50. percentage S character. In case of sp hybrid orbital, it's absolutely 50. In case of sp2, if you want to calculate percentage S character in case of sp2, one S orbital divided by total 3 orbitals have participated multiplied by 100. So percentage S character here will be 33%. Right? And in case of sp3 hybrid orbital, percentage S character, one S orbital has participated divided by total 4 atomic orbitals have participated multiplied by 100. The value comes out to be 25%. So 25% S character here. 25% S character here. My dear students, just move from left to right. Just move from left to right. From SP, then SP2, then SP3. Have a look. When you move from left to right, try to understand. When you move from left to right, what is happening to bond angle? 180, 120, 109. Bond angle is decreasing. On moving from left to right, what is happening to percentage S character? Percentage S character is also decreasing. Percentage S character is also decreasing. Right? Percentage S character is also decreasing. On moving from left to right, bond angle is decreasing as well as percentage S character is decreasing. So what has to be the relation between bond angle and percentage S character? What has to be the relation between bond angle and percentage S character? Do remember bond angle, it is directly proportional to S character, and this S character, it is directly proportional to electronegativity. As I told you, your S orbitals, they have got maximum electronegativity, followed by P, followed by D, followed by F. So more the S character involved in the orbital, involved in the hybrid orbital, more will be its electronegativity. As simple as that. Right? This is one very, very, very important statement which I'll frequently use, people. I believe it's clear. I believe it's clear. Yeah? Let me know in the chats. Let me know in the chats if all these things are clear till here. Right? This is something which I wanted to show. Now, people, tell me one thing. I believe this point is clear to everyone. Electronegativity is directly proportional to percentage S character, which is also directly proportional to bond angle. Perfect. This particular statement is absolutely clear. Number one. Number two. If I want to define the electronegativity of hybrid orbitals, how many different types of hybrid orbitals you have? sp hybrid orbitals, sp2 hybrid orbitals, sp3 hybrid orbitals. We calculated percentage S character everywhere. More the S character, more the electronegativity. So, in case of your sp hybrid orbital, percentage S character is 50. sp2, 33.33%, 25%. More the S character, more the electronegativity. So, if I'll be having sp hybrid orbital, sp2 hybrid orbital, and sp3 hybrid orbital, if I ask you to arrange these hybrid orbitals on the basis of their electronegativity, this is going to be the electronegativity order. The electronegativity of sp hybrid orbital will be maximum because of its more S character. Now we will try to understand. Look at this particular structure. I want you guys to look at these two carbon atoms. Okay? If you look at this particular carbon, how many sigma bonds it's forming? 1 sigma, 2 sigma. 2 sigma means sp. 3 sigma means sp2. 4 sigma means sp3. You know it, right? So if I ask you what is the hybridization of this particular carbon, it is basically sp hybridized. How many sigma bonds this particular carbon is forming? 1, 2, and 1 with hydrogen. 3 sigma. So it is sp2 hybridized. Correct? I believe this is clear. This is sp hybridized. This is sp2 hybridized. Now tell me. sp, more electronegativity. More S character, more electronegativity. So I would say the electronegativity of this particular carbon will be more. If electronegativity of this particular carbon is more, it has got more tendency to attract this bonded pair of electron towards itself. If it has got more tendency to attract this bonded pair towards itself, I would say it carries delta negative. This carries delta positive. Do you see a partial polar character got developed here in the molecule? Do you see? Do you see a partial polar character got developed in this molecule? And what is the logic behind that? A partial polar character got developed due to the electronegativity difference. And what is the cause of electronegativity difference? The cause of electronegativity difference is the difference in the hybridization. Yes, The difference in the hybridization. So what I'm trying to convey here, the molecule, it can become partially polar. The molecule can become partially polar because of difference in the hybridization. Because of difference in the hybridization. Because of the difference in the electronegativity. I hope this is clear. Okay. Someone is continuously spamming the chats. Sir, please take our doubts. What doubts you're asking? You're asking about the inert pair effect. I'm not teaching you the inorganic right now. I'm teaching you GOC, right? So if you have any doubt related to GOC, just ask me that. I'm not going to divert from my topic. Okay? When I will teach inorganic, I'll teach you in detail. Not now. So you cannot ask the random doubts here. You cannot ask me right now something from physical. If you have doubt related to this topic, ask that. Nothing apart from that. Okay? I hope it's clear. All right, people. I believe every single thing is clear till here. Okay? I believe every single thing is clear till here. Now, there are a few more things which I would want to share with you. There are a few more things which I would want to share with you. Okay? There is one more point. There is one more point. I'm going to write a statement. The statement is very simple and try to understand. The statement is simple and try to understand. Positive charge on an electronegative element. Positive charge on an electronegative element makes it more electronegative. Positive charge on an electronegative element makes it more electronegative. Now you must be thinking, what is meant by that? What is meant by that? Have a look. I told you people, your electronegativity, it is inversely proportional to size. It is inversely proportional to size. Imagine that this is oxygen. Imagine that this is O positive. This is O positive. The atomic number of oxygen is 8. So there will be 8 electrons as well as 8 protons. 8 electrons as well as 8 protons. Now you have taken 1 electron out, so there will be 7 electrons, but still there will be 8 protons. Still there will be 8 protons. Among these two, which one has got more effective nuclear charge? Where is the effective nuclear charge more? It's simple, guys. Here, the 8 protons were holding 8 electrons. Now the same 8 protons are holding only 7 electrons, right? So on these 7 electrons, I would say the force of attraction from the nucleus will be more. Yeah. Initially, 8 protons were holding 8 electrons. Now the same 8 protons, they are only holding 7 electrons. Right? The force of attraction experienced by these 7 electrons will be absolutely more. Due to which, what will happen to size? Size will shrink, it will decrease. So among these two, which one will have more size? O will have more size than O positive. Right? Okay? Right, people? Now, since I got to know about the size, you know, size is inversely proportional to what? Size is inversely proportional to electronegativity. Lesser the size, more the electronegativity. This one, O positive, has got lesser size. So its electronegativity will be more. So electronegativity of O positive will be absolutely more than that of electronegativity of O. So what happened? Positive charge on an electronegative element. Is it increasing its electronegativity? Absolutely, it's increasing its electronegativity. Absolutely, it's increasing its electronegativity. I hope this particular point is also clear. Positive charge on an electronegative element makes it more electronegative. Okay? Now, people, there is one more basic thing which you must know. I'm just dealing with the basics right now. I did not start the topic yet. I'm just dealing with the basics. Right? I did not start the topic yet. These are few cyclic compounds, right? These are few cyclic compounds which I have. My dear students, try to understand this particular carbon. How many bonds it's forming? Don't tell me it's forming 2 bonds. It's forming 4 bonds, right? This is hydrogen. This is one more hydrogen. It's forming 4 bonds. So how many sigma bonds? 4 sigma bonds it's forming. If it is forming 4 sigma bonds, tell me the hybridization of this particular carbon. It's sp3. Similarly, this particular carbon, it's attached with 2 other hydrogen atoms as well. So hybridization of this carbon is also sp3. This will be also sp3. Even this will be sp3. Right? All the selected carbons, they have got the hybridization of sp3. Now, in case of sp3 hybridization, what is the angle? Angle has to be under 9 degree 28 minutes. Right? Everywhere it's sp3. So the angle has to be, the bond angle has to be everywhere 109 degree 28 minutes. But my dear students, if you try to analyze this particular bond, does it look like 109 degree 28 minutes? It does not look like 109 degree 28 minutes. It will be just 60. This particular bond angle, it will be 60. It's not 109 degree 28. It has to be 109, but it is just 60. If I ask you what was the expected bond angle here, expected bond angle was 109 degree 28 minutes. But actual bond angle, it is just 60. It is just 60. Look at this particular molecule. This is also sp3 hybridized, right? So if I ask you the bond angle between these two, it appears to be 90. It appears to be 90. It was supposed to be 109 degree 28 minutes. But how much it is? Actually, it's 90. Actually, it's 90. Any such molecule in which the expected bond angle and the actual bond angle, they are different. Any such molecule in which the expected bond angle and the actual bond angle will be different, we say that particular molecule is under angle strain. So this particular molecule, it is under strain. This particular molecule, it is under strain. This is also under strain. This is also under strain. So all these molecules are under strain. Now, due to strain, what is going to happen? You must be thinking, okay, fine. All these molecules are under angle strain. Their expected and actual bond angles are different. That is the reason why I'm saying all these molecules here, they are under strain. They are under angle strain. Now, what is the consequence of that? What will happen due to angle strain? Try to understand what will happen due to angle strain. I'm making this particular molecule here. Here I'm making it. Okay? Look at this particular carbon. Look at this particular carbon. This carbon has got 2 hydrogen atoms attached with them, right? First of all, let me tell you, these 2 bonds, yellow colored bonds, these are what I call as endocyclic bonds. These are what I call as endocyclic bonds. And these 2 particular bonds with hydrogen, they are what I call as exocyclic bonds. Exocyclic bonds. Now tell me one thing. This particular bond angle should have been 109. It should have been 109. But how much it is? It is just 60. It is just 60. It should have been like this, but it is like this. It should have been 109, but it's 60. My dear students, that means if this endocyclic bond angle, it has decreased basically. From 109, it has decreased to 60. If this particular bond angle has decreased from 109 to 60, that means what would have happened to the exocyclic bond angle? What would have happened to this particular bond angle? This particular bond angle, is it going to be 109 or more than that? It will be more than that. It will be more than that. So can I say due to angle strain, this particular bond angle will be more? Right? If see, this particular bond angle, it was supposed to be 109, but it's 60. If this is decreasing, that means the outer part will be increasing. So this bond angle would have increased. Few minutes back, I told you, bond angle is directly proportional to what? Electronegativity. More bond angle, more electronegativity. So here the exocyclic bond angle, this particular bond angle, it has increased. So I would say the electronegativity of this particular carbon, it will be more than expected. It will be more than expected, right? Because you know, bond angle is basically directly proportional to electronegativity. If this particular bond angle is increasing, that means electronegativity of this carbon will be more than expected. Simple. Okay? It will be more than expected. Now people, if I ask you something like this, look at all these selected carbon atoms. Look at all these selected carbon atoms. Tell me which carbon atom will be the most electronegative. Among these carbon atoms which are selected here, among these carbon atoms, which carbon atom is more electronegative? You should be able to answer this. You should be able to answer this. More angle strain, more the angle strain, or let's keep it simple. Let's keep it simple. More the difference between expected and actual bond angles. More the difference between expected and actual bond angles. More is going to be the angle strain. More the angle strain, more is going to be the exocyclic bond angle. more the exocyclic bond angle, more is going to be the electronegativity. So can I simply say that the expected and actual bond angle difference here is more? So I would say electronegativity of this particular carbon will be maximum, followed by this, followed by this, followed by this. Is this point clear to you? Quickly. Quickly, people. Yeah, I believe it's clear. I believe it's clear. I believe it's clear. Now try to understand this particular scenario. This is one molecule here which I've taken, right? My dear students, over here, as you can see, it is a 3-membered ring. Here it is a 4-membered ring, right? If you particularly look at 3-membered ring, look at the carbon of this 3-membered, look at the carbon of this 4-membered. If I ask you whether their electronegativities will be same or different, let me know in the charts. Whether the electronegativities of these two carbon atoms, whether it's going to be same or different, what do you think? Quickly. Whether it's going to be same or different, quickly, quickly. Electronegativities of these two carbon atoms, is it going to be same or different? Say it in the charts. Same or different? Say it in the charts, quickly. It is going to be different, people. It is going to be different, right? Because this is a 3-membered ring. It is under more angle strain. 4-membered ring, comparatively less angle strain. More the angle strain, more the electronegativity. So I would say electronegativity of this particular carbon will be more. If electronegativity of this particular carbon is more, it will attract the bonded pair towards itself more. So this particular carbon gets delta negative, this particular carbon gets delta positive. So can I say due to the difference in the angle strains, again a partial polar character got developed here? Yes. Yes, I can say that. Due to the difference in the angle strains of these two particular rings, a partial polar character got developed here. Correct? I believe this is also clear to everyone. Now, people, moving on to the actual stuff. Moving on to the actual stuff. Now do remember. Now do remember. I'm sorry. As you know, I'm not completely well. Now try to understand. Okay. Now, guys, there are few simple types of questions which are asked. What are those simple type of questions? You will be asked the stability of charges on different elements. You will be asked to compare the stability of charges on different elements. For example, there will be a question. There will be few elements which are given to us. Few elements. For example, carbon, nitrogen, oxygen, fluorine. Negative charge, negative charge, negative charge, negative charge. You'll be asked, where is the negative charge more stable? Something like this. For example, there are few elements like this: carbon, nitrogen, oxygen, fluorine, right? Positive, 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 positive. You'll be asked, where is the positive charge more stable? How do we tackle these sort of questions? My dear students, just two things you have to remember. Just two things. Whenever you are supposed to compare the stability of the charges on the elements which belong to the same period, whenever you are supposed to compare the stability of the charges on different elements which belong to the same period, at that point of time, you will prioritize the concept of electronegativity. You will give your answer as per electronegativity. Whenever you have to compare the stability of the charges on the elements which belong to same period, at that point, you will give priority to electronegativity. Electronegativity dominates over volume charge density at that point of time. Electronegativity dominates over volume charge density at that point of time. Just remember few things. Negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element. And positive charge is more stable on less electronegative element. Just two things you have to remember. Whenever you have to compare the stability of the charges on the elements which belong to the same period, electronegativity dominates over volume charge density. You will give your answer as per electronegativity. Just two things you have to remember. Negative charge is more stable on more electronegative. Positive charge is more stable on less electronegative. That's it. That's it. Believe it's clear. I believe it's clear. I'll show its significance in some time. I'll show its significance in some time. Now, my dear students, there is one more statement. Look at this particular statement. Look at this particular statement. Have a look. Have a look properly. This carbon is having positive charge here. Over here, oxygen is having positive. Oxygen is having positive. I told you a few minutes back. Positive charge is more stable on less electronegative element. First of all, look at this. Carbon and oxygen, they belong to same period. Right? Now, what should be your answer? If I ask you where is the positive charge more stable, you should say positive charge is more stable on less electronegative element. Carbon is less electronegative as that of oxygen. So positive charge should be stable here. But in this particular case, positive charge is stable here. Why is that? You have to look at the octet as well. Is the octet of carbon complete? No. It just has got 6 electrons in its outermost shell. Here, 2, 4, 6, 8. It has got 8 electrons in its outermost shell. The octet of oxygen here is complete. The octet of carbon is incomplete. Okay? So, do remember this particular statement as well. Positive charge can become more stable. It can become more stable as over here. It can become more stable on more electronegative element. But when? When its octet becomes complete. When its octet gets completed. Right? You have to take care of these small things, people. You have to take care of these small things. Okay? You have to take care of these small things. Now, first point I told you, whenever you have to compare the stability of the charges on different elements which belong to the same period, you will give priority to electronegativity. Right? Negative charge is more stable on more electronegative. Positive charge is more stable on less electronegative. But whenever you have to compare the stability of the charges on the elements which belong to the same group, at that point of time, you are not going to prioritize electronegativity. You will be prioritizing volume charge density. Volume charge density at that point of time, it dominates over electronegativity. For example, chlorine, bromine, iodine, they do not belong to same period. They belong to same group. So if you want to compare their charge, if you want to compare the stability of the charges, you won't be comparing it on the basis of electronegativity. No, you'll be comparing it on the basis of volume charge density. You know already, volume charge density, that is inversely proportional to stability. Volume charge density, that's inversely proportional to stability. Let's do some questions. It'll be absolutely clear to you. It'll be absolutely clear. Try to understand. Can you let me know where is the negative charge more stable? First of all, identify these elements, they belong to same group. So VCD. VCD, which is charge divided by size. Charge everywhere is same. Look at the size. On moving from top to the bottom, size increases. More the size, less the volume charge density. And you know, your volume charge density, that's inversely proportional to stability. Less the volume charge density, more the stability. Now try to understand. Iodine has got maximum size, less VCD, more stable. So I'll say negative charge is more stable here. Simple, right? Look at this particular case. Fluorine, bromine, iodine. What do you think? They are from same group. Again VCD. More size, less VCD, more stability. So positive charge is more stable on iodine here. Getting it? Let's try to do some questions which will make this concept absolutely clear. And few things which you have to note one by one. Try to understand, guys. Look at the first question. Carbon, nitrogen, oxygen, fluorine. Where is the positive charge more stable? First of all, try to identify. All these elements, they belong to same period. Electronegativity plays a role. Positive charge is more stable on less electronegative element. Now, among these, which one is less electronegative? Carbon. So this is the stability order. Simple. Carbon, nitrogen, oxygen, fluorine, carrying negative charge. All these carbon, nitrogen, oxygen, fluorine, they belong to same period. Electronegativity. Negative charge is more stable on more electronegative. Fluorine is more electronegative than oxygen, then nitrogen, then carbon. This is the stability order. Done and dusted. Right? Look at the next case. Sulfur carrying negative, chlorine carrying negative. They belong to same period. Sulfur, chlorine. Electronegativity plays a role. Negative charge is more stable on more electronegative. Right? Negative charge is more stable on more electronegative. Chlorine is more electronegative than sulfur. Right? So, negative charge is more stable on more electronegative. Simple. Look at the next one. Oxygen, sulfur, SET. Oxygen, sulfur, SET. They belong to same group. They belong to same group. And in the group, and my dear students, in the group, what is going to happen? In the group, what is going to happen? You are going to prioritize VCD, volume charge density. So your answer has to be in terms of VCD. Your answer has to be in terms of VCD. So tell me what has to be the answer of this question. Tell me what has to be the answer of this question quickly. Quickly. Your volume charge density is equal to charge divided by size. Charge divided by size. Down the group, size increases. Size increases. So this one has got the maximum size. Least VCD. Least VCD means more stability, right? So negative charge will be stable here. This is going to be the stability order. Yeah? I believe it's clear. I believe it's clear. Look at this particular scenario. Tell me the answer of these questions now. Tell me the answer of these questions. Nitrogen, phosphorus, arsenic, antimony. They belong to same group. Volume charge density. Volume charge density. More size, less volume charge density, more stability. Right? Oxygen, sulfur, both carrying negative. Oxygen, then sulfur. Same group. Down the group, size increases. Sulfur has more size, less VCD, more stability. Right? Clear, people? Let me know quickly in the chat if it is clear. Now, people, this one is very simple. This is single bonded carbon carrying positive. This is double bonded carbon carrying positive. Triple bonded carbon carrying positive. Where is the S character more? Triple bonded carbon, it has got more S character than that of this double bonded. More S character means more electronegative, right? And you know positive charge is more stable on less electronegative. This one is least electronegative. So positive charge will be maximum stable here. Simple and basic. What about the stability of these? Carbon carrying negative, single bonded, double bonded carbon, triple bonded carbon carrying negative. More S character, more electronegativity. Negative charge is more stable and more electronegative. So this is the stability order. Done and dusted. Right? Clear? Look at these particular questions. Look at these particular questions. What do you think? What do you think about these, my dear students? Try to understand. Carbon carry this negative, this carrying negative, this carrying negative, this carrying negative. Now, 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring. Which one is more electronegative? First one. Negative charge is more stable and more electronegative because of more angle strain. Right? Positive charge. Positive charge is more stable and less electronegative. Less electronegative. Tell me among these two. Carbon carrying negative, nitrogen carrying negative. What do you think? Carbon and nitrogen, they belong to same period. So which concept? Electronegativity plays a role here. Electronegativity plays a role here. And you know, negative charge is more stable and more electronegative. You know, negative charge is more stable and more electronegative. So where is the negative charge more stable? On carbon, on nitrogen? What do you think? I want answers from you. I want answers from you quickly. Quickly, people. Quickly, everyone in the chats. Where do you think will be the negative charge more stable? Say it quickly. Say it quickly. Say it quickly. Normally, if you look at the normal procedure, my dear students, this is carbon carrying negative, this is nitrogen carrying negative. They belong to same period. So you have to give your answer on the basis of electronegativity. And you know, among carbon and nitrogen, which is more electronegative? Nitrogen. And negative charge has to be more stable or more electronegative. So this has to be the order. But this is not the order. The order is reverse. The order is reverse. Why is that? Why is that? People, let me tell you, this is sp hybridized carbon. And this one, it is sp3 hybridized nitrogen. Do remember, electronegativity of sp hybridized carbon is more than that of sp3 hybridized nitrogen. If you look at the values as well, the electronegativity of this particular carbon is 3.25, here it is 3. So which one is more electronegative? sp hybridized carbon is more electronegative than that of sp3 hybridized nitrogen. Okay, and you know, negative charge is more stable and more electronegative. So this particular carbon is more electronegative. So negative charge will be more stable there. Okay, do remember this particular special case. Do remember this particular special case. Now, I just taught you two concepts. One is electronegativity, one is VCD. Now, on the basis of these concepts, what kind of different types can be asked? What kind of different questions can be asked? out of these two concepts. My dear students, questions can be asked on the basis of acidic strength. The same concept which we discussed. I can use this concept to check the acidic strengths of different species as well. How exactly? Try to understand. Imagine I've got an acid HA, right? This acid, it has got tendency to lose H positive. Imagine that it's donating H positive, right? And after donating H positive, it's getting converted into A negative. Okay? If HA is the acid, after the removal of H positive, it got converted into A negative. This A negative I'll be calling as conjugate base of the acid. Okay, I took an acid. After the removal of H positive, it got converted into A negative. A negative I'll be calling as conjugate base of this particular acid. Now, do remember one simple thing. Strength of acid is directly proportional. Strength of acid is directly proportional to what? Strength of acid is directly proportional to what? It is directly proportional to the stability of its conjugate base. It is directly proportional to the stability of its conjugate base. More stable the conjugate base, stronger is going to be the acid. Stronger is going to be the acid. Stronger is going to be the acid. Okay? Right? Strength of the acid is directly proportional to what? Stability of its conjugate base. Perfect. More stable the conjugate base, stronger is going to be the acid. As simple as that. Let's try to use this concept. Let's see what kind of questions can we solve. One by one. One by one. Among these two acids, ROH, RSH, which one is more acidic? Which one is more acidic? Try to understand how exactly am I going to solve them. Right? ROH, RSH, which one is more acidic? Take H positive out from here. When you take H positive out from here, the conjugate base becomes RO negative. When you take H positive out from here, the conjugate base becomes RS negative. Now, these are the conjugate bases. These are the conjugate bases which I have drawn over here. Now, check the stability of these conjugate bases, people. Oxygen carrying negative, sulfur carrying negative. Oxygen and sulfur, same group. VCD plays a role. More size, less VCD, more stability. So, this is the stability order of the conjugate bases. More stable the conjugate base, stronger is going to be the acid. So, this is the acidic strength order. Done? Why you are telling ROH is going to be more acidic? Yeah, I mean, use the concept which I told you right now. Use the same concept. Why you are involving some other concepts? Do not involve some other concepts. Whatever I'm telling you, just remember them, utilize them, that's it. Right? Okay. Among these four, which one is more acidic? So take H positive out from here, it becomes CH3 negative. Take H positive out from here, it becomes NH2 negative. Right? Take H positive out from here, it becomes OH negative. Take H positive out from here, it becomes F negative. So what did I do? I made the conjugate bases of these acids. Now, stability order. Carbon carrying negative, nitrogen negative, oxygen negative, fluorine negative. They belong to the same period. Electronegativity plays a role. Negative charge is more stable and more electronegative. Negative charge is more stable and more electronegative. So this is the order of the stability of the conjugate bases. And whatever is the order of the stability of the conjugate bases, same is going to be the order for their corresponding acids. Right? Same is the order of their corresponding acids as per their strengths. Correct? Look at this one. Take H positive out from here, it becomes OH negative, oxygen carrying negative. Right? Take H positive out from here, it becomes SH, sulfur carrying negative. Perfect. These are the conjugate bases of these two acids, for example. Right? Now try to understand. Oxygen negative, sulfur negative. Oxygen and sulfur, same group, volume charge density. More size, less VCD, more stability. This is the stability order of the conjugate bases. So same is going to be the order of their acidic strengths. Done and dusted. The next part. Take H positive out, this carbon will get the negative. Take H positive out, this carbon gets negative. This carbon gets negative. Triple bonded carbon, more electronegative. Negative charge is more stable and more electronegative. Negative charge is more stable and more electronegative. So the stability of conjugate bases as well as strength of acids. This is going to be the order. This is going to be the order. Simple. Simple, nothing to do, nothing to remember. Among these two, which one is more? Which one is more acidic? Which one is more acidic? See, if you take H positive out from here, this carbon will be getting negative. If you take H positive out from here, this becomes like this. This becomes like this. Now, this is sp hybridized carbon. This is your sp3 hybridized nitrogen. The electronegativity of sp hybridized carbon is more. Negative charge is more stable and more electronegative. So this is the order of their stability of conjugate bases, as well as this is going to be the order of their strength of the acids. As simple as that. My dear students, is it clear? Let me know in the chats, is it clear? Is it clear? The basics which I needed to start the first concept, that is inductive effect, that is done and dusted. So let me know once in the chats if every single thing is clear till here. Let me know once in the chats if every single thing is clear. Yes. I want everyone to say it. I want everyone to say it if all the things are clear or not. Yeah, done and dusted. I want everyone to say it if all the things are clear or not. Quickly, quickly, quickly. Then only I'll start this particular topic. This is again very important. And now you will see different types of questions on inductive. Whatever questions can be asked from inductive effect, everything I'll be showing right now. Okay. But first, I want everyone to say it if every single thing is clear or not. If you're not going to say it, I'll end the session right now. If you're happy with that, I'm also happy with that. You want me to do that? Wow, I cannot read your chats without my specs. It's all blurry. Okay, by the way, a lot of people are waiting for solution chapter, right? Solution chapter, I think I'm not going to take on YouTube. I'll take a special class for a solution chapter. Special class that will happen on Unacademy platform. That is absolutely free for everyone. Okay, I'll share the link in the Telegram. I'll share the link in the Telegram. That chapter I'm planning to take on the special class. Okay, perfect. Let's start with the inductive effect then. Let's see what this inductive effect exactly is all about. See guys, first of all, let me write its definition. What is inductive effect all about? It is the phenomenon. It is a phenomenon of partial polarization. The phenomenon of partial polarization of a carbon chain. Of a carbon chain. Due to the transmission of sigma electrons. Due to the transmission of sigma electrons. When an atom or group of atoms. When an atom or group of atoms is attached towards the chain. What does it mean? Let's have a look. This is something very important, guys, okay? This is something. From here, we are going to start basically the things. Whatever I was teaching you now, that was complete basics. That was basics required to start the organic. So this is the first topic. Let's try to cover this. Have a look now. Inductive effect. My dear students, to make this inductive effect very much clear to you, let me take a carbon chain. Let's say this is the chain of carbon atoms. It's the chain of carbon atoms. right? Okay. So over here, there'll be two hydrogens, right? Over here, there'll be two hydrogens here also, okay? So let me write it like this. Let's say this is one carbon chain, leave the hydrogens aside, whatever is the number, okay? So first of all, imagine this is the carbon chain, and right here, look at this particular hydrogen. Look at this particular hydrogen. I'm just showing you one hydrogen. I'm just showing you one hydrogen here. Actually, there'll be three hydrogens, right? I'm just showing you one hydrogen, right? Now, my dear students, in this carbon chain, what kind of bonds do we have? We just have got sigma bonds. So if I ask you what kind of electron density is here in the carbon chain, there is sigma electron density in the carbon chain. There is sigma electron density in the carbon chain, right? Now, what exactly am I going to do? Let me just remove this hydrogen, and in place of hydrogen, let me do one thing. In place of hydrogen, let me place an atom or group X, an atom or group of atoms X. Let me do that, okay? Then again in one more scenario, let me do one more thing. Instead of this hydrogen, I'm attaching Y, a group or atom Y, okay? Why is it? Try to understand. What I exactly did, I took a carbon chain, in place of hydrogen, at one point of time, I attached an atom or group X, and in one more scenario, in place of this hydrogen, I attached Y over here, which can be atom or group of atoms. Okay. Now try to understand. Imagine, for example, electronegativity of X is more than that of electronegativity of carbon. Imagine X is more electronegative than this carbon. Imagine X is more electronegative than this particular carbon. Akilan, bro, is this the way to talk? Is this the way to talk? Just tell me that first of all. Who you're talking to? What does it mean? Whether my question is visible or you are ignoring? What does that mean? Are you talking to some roadside Romeo? These are free lectures, by the way. You know it. You should be knowing it. Right? This is something which I'm teaching absolutely free of cost. First of all, have some manners to talk to a teacher, okay? Whosoever you are. All right. So what exactly I've done? I've removed this hydrogen, and in place of hydrogen, I have kept an atom or group X. I'm assuming X is more electronegative than that of carbon. My dear students, if X is more electronegative than that of carbon, if X is more electronegative than that of carbon, what will happen? That means X will have more tendency to attract this sigma bonded pair towards itself. As simple as that. Right? Try to understand. This is X. I'm assuming X is more electronegative than that of carbon. If X is more electronegative, that means X has got more tendency to attract the sigma bonded pair towards itself. If X has got more tendency to attract the sigma bonded pair towards itself, so can I say there'll be shift of sigma electrons towards X? If there is shift of sigma electrons towards X, can I say this X will get delta positive and this carbon will get delta positive? Sorry, this X will get delta negative and this carbon will get delta positive. Right? Now, my dear students, the carbon which is over here, it got delta positive. Can I say this delta positive is going to attract this particular sigma bonded pair towards itself, due to which again there'll be shift of this sigma electrons also, right? So this carbon will be also getting delta positive. Similarly, this delta positive will be attracting this sigma electron pair towards itself, right? Due to which there is shift of sigma electrons, and this carbon again gets delta positive. So what happened over here? What happened over here? My dear students, when I attached a group towards a carbon chain, Can I say transmission of sigma electrons took place? Transmission of sigma electrons took place, by means of which the chain got partially polarized. The phenomenon in which the carbon chain gets partially polarized. The carbon chain gets partially polarized due to the transmission of sigma electrons when an atom or group of atoms is attached to the carbon chain. This particular phenomenon is something which you call as inductive effect. This is something which you call as inductive. Look at this particular case. Look at this particular case. Imagine electronegativity of carbon is greater than electronegativity of Y. Imagine electronegativity of carbon is more than that of Y. So what is going to happen? Carbon is going to attract this sigma bonded pair towards itself, due to which there will be moment of shift of sigma electron density towards carbon, due to which this carbon gets delta negative and this Y gets delta positive. Now this delta negative on carbon is going to repel this particular bonded pair. If it repels the bonded pair, so this particular bonded pair will shift in this direction, So this carbon gets delta negative. Now this delta negative on carbon is going to repel this particular bond pair as well towards the other carbon, due to which this particular carbon also gets delta negative. So what is happening? What is happening? Can I say, again in this particular case, if you look at the carbon chain, I'll say transmission of sigma electrons is taking place. Transmission of sigma electrons is taking place, due to which the chain got partially polarized when an atom or group of atom was attached to the chain. So this particular phenomenon is something which I call as inductive effect. I believe it's clear. I believe it's clear. My dear students, look at this scenario now. Look at a proper scenario now. If I ask you, is this particular atom or group increasing the electron density, increasing the sigma electron density inside the chain, or decreasing it? What do you think? Can I say it seems like this? This X is pulling the sigma electrons towards itself, right? So I should be calling it as electron withdrawing, right? Look at this particular scenario. This Y, as if this Y is pushing the sigma electrons in the chain. This Y is pushing the sigma electrons in the chain, right? So should I be calling this as electron withdrawing or electron donating? I should be calling this electron donating. My dear students, that particular group which decreases the sigma electron density in the carbon chain, we say that particular group shows minus inductive effect. That particular group which decreases the sigma electron density in the chain, that particular group shows minus inductive effect. And that particular group which increases the sigma electron density in the chain, we say that particular group shows plus inductive. So this X, it is showing minus I effect. Minus means electron withdrawing. Whatever minus it is. Minus I, minus H, minus M, whatever. We are going to study afterwards, right? Minus means electron withdrawing. Perfect. So this particular group, it is decreasing the sigma electron density in the chain. This particular group, it is increasing the sigma electron density in the chain. I believe it's clear. So do remember, that group or atom which decreases the sigma electron density in the chain, that shows minus I. That group of atom which increases the sigma electron density in the chain, we say that shows plus I. Okay, plus I. Now people, there are few things which you need to know. Then we can do a lot of questions. Few more things. My dear students, plus I and minus I, they are relative to each other. They are relative to each other. What does that mean? Plus I and minus I, they are relative to each other. What does that mean? What does that mean? Try to understand. First of all, if you look at this particular cyclic ring, it contains 3 carbon atoms. I'm selecting this particular carbon. This contains 4 carbon atoms, right? Now, is the electronegativity of these 2 carbons same or different? It is different. This carbon will be more electronegative. This carbon will be less electronegative. If this carbon is more electronegative because of more angle strain, there will be shift of sigma electron density in this particular direction, due to which it gets delta negative, this gets delta positive, correct? Now, my dear students, if I talk about this particular group, do you think it is electron withdrawing here or donating? This is withdrawing. It is withdrawing group. If you talk about this particular group, is this particular group withdrawing or donating? This is donating. This is withdrawing. So I'll say this particular group, it shows minus I. This particular group, it is donating. It shows plus I. So can I say something like this? This particular group over here, it is showing minus I effect with respect to this particular group. And this particular group is showing plus I effect with respect to this particular group. So plus I and minus I. How do I say they are relative to each other? This particular group, it is showing minus I with respect to this one. And this particular group, it is showing plus I with respect to the other one. So both the ones, plus I and minus I, they are relative to each other. They are relative to each other. Right? Look at this particular case. Look at this particular carbon. Hybridization of this carbon is sp. Hybridization of this particular carbon is sp2. Right? More s character, more electronegative. So this carbon is more electronegative. So this particular sigma bonded pair will shift in this direction. It will shift in this direction. So delta negative, delta positive. Now, if I ask you something like this, what about this particular group here? This particular group. Do you think this particular group is sigma electron donating or sigma electron withdrawing? It is sigma electron withdrawing. So I'll say this particular group shows minus I. And what about this one? It at the same time shows plus I. One shows minus I and one shows plus I. Right? So can I say something like this? Over here again, this particular group is showing minus I with respect to this one. And this one is showing plus I with respect to this one. So plus I and minus I, they are what? They are relative to each other. One is minus I with respect to the other group. The other group is plus I with respect to the previous one. That is something which I wanted to convey. This is one of the points. Now few more points. All the cationic groups, they are minus I showing group. These are all cationic groups. A group carrying positive charge is called as cationic group. All the cationic groups, they'll always show minus I. They'll be always electron withdrawing. They'll always show minus I, right? They'll always show minus I. Point number one. Point number two. Minus I power of cationic group is always greater than that of minus I power of neutral group. So whenever you have to compare the minus I power of cationic group and minus I power of a neutral group, minus I power of cationic group will be always greater than that of minus I power of neutral group. One more point. First, all the cationic groups, they show minus I. Now, when you have got a cationic group as well as the neutral group, which one will have more minus I power? Cationic group always has got more minus I power than that of neutral group, right? All the halogens, your group 17 elements, they show minus I. All the halogens, be it fluorine, chlorine, bromine, iodine, they show minus I, right? They show minus I. All these groups, they show minus I. Why do they show minus I? Look at this particular case as well. Imagine this particular group OH. Imagine this particular group OH is attached to the carbon chain. Let's say this is some carbon chain, right? And I'm attaching OH towards it. Attaching OH towards it. Try to understand. Among carbon and oxygen, which one is more electronegative? Oxygen. So oxygen will attract the sigma electron density towards itself. Delta negative, delta positive, delta positive, delta positive. So this particular OH group, it is withdrawing sigma electron density from the chain. It is decreasing the sigma electron density from the chain. It is decreasing the sigma electron density in the chain. So if it is decreasing the electron density in the chain, it's going to show minus I power, right? Imagine this NH2 is attached to the carbon chain. Imagine this is the carbon chain towards which NH2 is attached. Between carbon and nitrogen more electronegative. So it's again going to attract the sigma electron density towards itself. So minus I. Similarly, this is minus I. This is Cn. Imagine this is your carbon chain, right? With which you are attaching Cn. This is C triple bonded. This is your Cn, right? This is sp hybridized carbon. This is your sp3 hybridized carbon. Now, which one is more electronegative? This carbon is more electronegative. It's going to attract the sigma electron density towards itself. Due to which delta negative, delta positive, delta positive, delta positive. So this Cn group, it's also withdrawing sigma electron density. So it's again minus I showing group. So all these particular groups which I mentioned over here, they are minus I showing groups. They are minus I showing groups. They are minus I showing groups. Okay. If I ask you about this particular group, imagine this particular group is attached with a carbon chain. This is the carbon chain, right? Now, CO bond, it's polar. Oxygen will get delta negative, carbon will get delta positive. Now, this carbon delta positive, it's going to attract the sigma electron density towards itself, due to which this particular group becomes electron withdrawing. So it's showing minus I. right? Similarly, this is delta positive, this is delta negative. If it is attached to the carbon chain, again, this particular group will show minus I, right? This particular group, delta positive, this will minus I, this minus I. So all these groups which I mentioned over here, all these groups are going to show basically what? All these groups are going to show the minus I power, right? All right, I'll take coordination chemistry also. Don't worry. I hope this particular point, all these points are clear. Number one, all the cationic groups, they are going to show minus I effect. Minus I power of cationic group is greater than that of minus I power of the neutral group, right? Number two, all the halogens, they show minus I effect. And all these groups which over here, which are mentioned, they always show what? Minus I, right? Okay. Clear, people? Perfect, guys. Now there are few more things. Like I told you, all cationic groups, they show minus I power, minus I effect. Similarly, all the anionic groups, these are all the anionic groups carrying negative charge. They show plus I effect. Number one. Number two, plus I power, electron donating power of these anionic groups is always greater than that of plus I power of neutral groups. One more thing. Plus I power of anionic groups always greater than that of plus I power of neutral groups. Okay. All the alkyl groups, be it methyl, ethyl, propyl, right? All the methyl groups, they show plus I. Why is that? Look at this particular scenario. Among carbon and hydrogen, which one is more electronegative? Carbon. So this bond pair will shift towards carbon. So delta negative. So carbon is carrying negative. Basically. Look at this particular bond pair. There is a bond pair here. This negative will repel the bond pair, right? So there'll be a shift of this sigma electron density towards the carbon chain. So in the carbon chain, sigma electron density is increasing. That group which increases the sigma electron density in the carbon chain, that shows plus I. So it is showing plus I. So all your alkyl group, be it methyl, propyl, ethyl, whatever, they always show plus I effect. Right? Few more basic things, then we'll go to the questions, right? My dear students, plus I power of a group is directly proportional to the number of branches at the free valent carbon. Plus I power, it is directly proportional to the number of branches at the free valent carbon. What does that mean? See, imagine this is one group. It's a group, right? It's a group which has to be attached to the carbon chain. This is the carbon chain here. And towards this carbon chain, this group is attached, right? That particular carbon which is directly connected with the carbon chain, this is something which I call as free valent carbon. So this is free valent carbon. Here, imagine this is the carbon chain and this is the group which is attached with the carbon chain. That particular carbon which is attached with the chain directly, that's your free valent carbon. So free valent carbon. Plus I power is directly proportional to branching at the free valent carbon. Now, if I ask you whether this particular group will show more plus I or this particular group will show more plus I. Both are alkyl groups. Alkyl groups, they always show plus I. Now, which alkyl group will show more plus I? Where the branching at free valent carbon is more. Look at this particular carbon. It is having 1 plus 2. It is having 2 branches at the free valent carbon. This particular carbon, it is having 1, 2, 3. 3 branches exactly. So, wherever you see more branches at the free valent carbon, its plus I power will be more. So, plus I power for the second one will be definitely more than that of first one. I believe it's clear. This was first point. One more point. Now imagine if the branching is same at the free valent carbon. Then plus I power is directly proportional to number of carbon atoms in the branch. What does that mean? See, this is the free valent carbon, imagine, which is attached with the carbon chain. Here, this is the free valent carbon attached with the carbon chain. Here, it is the free valent carbon attached with the carbon chain, right? Now people, only one branch. This free valent carbon, only one branch. This particular free valent carbon, only one branch. So all these free valent carbons have got only one branch. Now if branching is same, only one branch attached with the free valent carbon. Now, which group particularly will have more plus I? Since this is alkyl group, alkyl, right? So they will show plus I. Now which will show more plus I? Wherein the branch contains more carbon atoms. Here the branch contains more carbon atoms, right? So the plus I power of this one will be maximum, followed by this one, followed by this one. Simple. If you talk about the isotopes of hydrogen, hydrogen has got different isotopes. Protium, deuterium, tritium, right? Protium, deuterium, tritium. Protium, deuterium, tritium. If you arrange these isotopes on the basis of plus I power, they show first of all plus I. Now, let me tell you, tritium shows maximum plus I power, followed by deuterium, followed by protium. Tritium shows maximum plus I power, people. Maximum plus I power, followed by deuterium, followed by protium among the isotopes of hydrogen. This is again something which you need to know. Okay. Well, after knowing all these things, let's try to identify. Let's try to identify a few things. Have a look. Arrange the following on the basis of their minus I. Now, among these four, which one will show more minus I power? More minus I power. You guys are going to tell me. Imagine this fluorine is attached with a carbon chain. Imagine this chlorine is attached with the carbon chain. Bromine attached with the carbon chain. Iodine is attached to the carbon chain. Now, which one is more electronegative? Fluorine, chlorine, bromine, or iodine? Fluorine. Right? Yes? Right, people? Yeah? Which one is more electronegative? Fluorine. So can I say fluorine will, since it's more electronegative, so it's going to attract the sigma electrons maximum towards itself from the carbon chain, right? So I'll say this fluorine is more electron withdrawing. More electron withdrawing means more minus I. So this is the minus I power. Clear? Fluorine attached with the carbon chain, oxygen attached with the carbon chain, nitrogen attached with the carbon chain. FON. FON. Right? Fluorine is more electronegative. It's going to attract more sigma electrons towards itself from the carbon chain. So more electron withdrawing. More electron withdrawing. More minus I. Cationic group, neutral group. Cationic group, neutral group. All the cationic groups, they show more minus I power. More minus I power. Cationic groups, they show more minus I power than that of neutral groups. Oxygen attached with the carbon chain, nitrogen attached with the carbon chain. Oxygen being more electronegative, more electron withdrawing, more minus I. Right? Look at this one. This carbon attached with the carbon chain. Here, this is the carbon. Here, this is the carbon. Right? Now, this carbon, it's sp hybridized. This is sp2 hybridized. This sp3 hybridized. Now, among these three, which one will be more electronegative? This carbon is more electronegative. If this is more electronegative, it's going to attract maximum sigma electron density towards itself. So it will show maximum minus I power. So this is the order of minus I here. Right? Okay. Right, people? Sir, in CD3, what is D? D means deuterium. That means in place of protium, you have used 3 deuteriums. Okay? I believe it's clear. I believe it's clear. So these sort of simple questions you should be able to solve. Now arrange them on the basis of their minus I. Arrange them on the basis of their minus I. 1, 2, 3. Among these three, which one will be having more minus I power? What do you think? What do you think? This is C double bond O. Delta positive, delta negative. Delta positive, delta negative. Right? Now imagine this is attached with a carbon chain. Imagine this is attached with the carbon chain. Imagine this is also attached with the carbon chain. Right? Now the electronegativity difference here, it is more than that of this electronegativity difference. So wherever electronegativity difference is more, there only more will be the positive charge on the carbon. So among this carbon and this carbon, where will be the intensity of positive charge more? I'll say intensity of positive charge is more here. Intensity of positive charge is more here because electronegativity difference is more here. If positive charge intensity is more here, it's going to attract more sigma electron density towards itself. So the minus I power will be like this. Simple. 1, 2, 3. Now, NF3NH3. NF3NH3. This is evident, right? Nitrogen carrying positive, phosphorus carrying positive, arsenic carrying positive, Sb carrying positive. All these elements, do they belong to same period or same group? Same group. VCD plays a role. VCD plays a role. Where is the positive volume charge density maximum? Size minimum, positive volume charge density maximum. And wherever positive volume charge density is maximum, that will show more minus I. Simple. Look at this one. Oxygen, sulfur, acetylene. Same group. Same group. Positive volume charge density is more in the one where the size is minimum. Oxygen has got minimum size. More positive volume charge density, more minus I power. Look at this one. NR3 positive, NH3 positive. NR3 positive, NH3 positive. So this is NR3 positive. Nr3 positive, and you have got NH3 positive. Normally, if you look, these are the alkyl groups, right? Alkyl groups show plus I. So you must be thinking these alkyl groups, they'll push the electrons towards nitrogen, due to which positive charge will be nullified, kind of thing. You'll be thinking like that. The case is reverse. See, alkyl. These are bulky groups. More repulsions. More repulsions means more bond angle. More bond angle means more electronegativity. So electronegativity of this particular nitrogen will be more than that of this one. If electronegativity of this particular nitrogen is more, it will be more electron withdrawing. Among these two, this one is more electron withdrawing. More minus I. I hope it's clear. I hope it's clear to everyone. Yes, I hope it's clear to everyone. Now guys, there's a series basically, plus I series and minus I series. I believe you all must be knowing about this, right? This is the minus I series. NF3 positive will show maximum minus I power, followed by Nr3 positive, followed by NH3 positive, followed by NO2, followed by Cn, followed by CHO, followed by COOH, F, Cl, Br, iodine, right? So this is the series, minus I series power basically, right? This is something which you have to remember. You can use any sort of mnemonic for this. Whatever you feel like making, you can make that on your own, right? Whatever you feel like making, you can make that on your own. This is the minus I power series. And similarly, this is the plus I power series. CH2 negative maximum plus I power, followed by NH negative, O negative, COO negative, 3 degree alkyl, 2 degree alkyl, 1 degree alkyl, SiH3, etc., etc. This is the plus I series over here. This is the plus I series over here. So this series, first of all, you have to remember. This series you have to remember. Both plus I series as well as minus I series. You can make any sort of mnemonic based on your choice. Okay? I'll show its application part now. I'll show its application part. Before showing the application part, do remember one more thing. Whenever you talk about the inductive effect, my dear students, inductive effect, it vanishes after third carbon atom. It vanishes after third carbon atom. For example, this is carbon, 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 and carbon, right? Now, you're attaching, for example, halogen over here. Halogen is electron withdrawing. So, delta negative, this will be delta positive. Now, the magnitude of delta positive will keep on decreasing. Magnitude of delta positive will keep on decreasing. So, inductive effect is distance dependent effect basically. And you are going to consider its effect till carbon number 3. Till carbon number 3. Okay? So, you have to remember this particular point as well. Both plus I and minus I, they are considered only up to 3 carbon atoms. As inductive effect, it is a weak effect basically. Okay? Remember this point also, it will be helpful for you. Now comes the application part of inductive effect. First of all, the first application of inductive effect. Inductive effect, with the help of inductive effect, you get to know about the stability of carbocations. You get to know about the stability of carbocations. See guys, stability of carbocation. Stability of carbocation. Let me tell you, carbocation is stabilized by plus I showing groups. Carbocation is stabilized by plus I showing group. And it is destabilized by electron withdrawing, that means minus I showing groups. So plus I showing groups are going to stabilize the carbocation, and minus I showing groups, they are going to minus I showing groups, they are going to destabilize the carbocation. Why is that? Why is that? Imagine a plus I group is attached with the carbocation. Imagine this is the carbon carrying positive charge. And over here, you have got some plus I showing group. Plus I showing group. What is going to happen? It is going to push the sigma electron density towards carbon, due to which the magnitude of positive charge will decrease. If the magnitude of positive charge is decreasing, lesser the charge, more is the stability, right? Lesser the charge, more is the stability. Now, if the same carbocation is attached with a minus I showing group, this is electron withdrawing, it's going to attract the sigma electrons towards itself, due to which the intensity of positive charge on this carbon will increase. And more the charge, lesser the stability, right? More the charge, lesser the stability. Simple. So plus I showing groups, they are going to increase the stability of carbocation. Minus I showing groups, they are going to decrease the stability of carbocation. Okay? Two things, and move on to the questions. Order of the stability. Single bonded carbon, double bonded carbon. Single bonded carbon, double bonded carbon. Quickly. Quickly. Quickly, which one? Where do you see positive charge more stable? Where do you see positive charge more stable? Quickly, guys, you should answer this question. Nomenclature is already taught. There is nothing left there. Where do you see which one is more stable, people? Quickly. Why are you waiting for this long, guys? You should answer this question easily. Positive charge is more stable on less electronegative. This is single bonded, this is double bonded. More S character, more electronegative, less electronegative. Positive charge is more stable on less electronegative. Khadam? Right? Look at this particular carbocation. This is plus I showing, plus I showing, plus I. All alkyl groups are plus I showing. Plus I, plus I, plus I. Over here, there are more plus I showing groups. And plus I showing groups, they increase the stability of the carbocation. So this is the stability order of the carbocation. Right? This is the stability order of the carbocation. Perfect. This is the stability order of the carbocation. Now, among first, second, and third, which one is more stable? Where do you see the stability more? You have to be quick now. You have to be quick. This is the carbocation here, right? CH3, CD3, NO2. NO2 shows minus I. This shows plus I. This shows plus I, right? Plus I groups, they increase the stability of carbocation. Now, A and B will be more stable than that of C. A and B will be more stable than that of C. Now, among A and B, which one is more stable? Which one is more stable? CD3 in that, I mean, I gave you an order. In that order, CD3 was having more plus I power, right? More plus I, so B is more stable than that A, then followed by C. Simple. Right? Perfect. Now, among these three, nitro group, and over here there is no nitro group. Nitro shows minus I, here also minus I. Minus I showing groups, they destabilize the carbocation. They destabilize the carbocation. No withdrawing group here, right? No nitro group here. No nitro group here. So A is maximum stable. Now among B and C, inductive effect, that is distance dependent. So where is inductive effect more prominent among these two? Inductive effect will be more prominent here. So C will be least stable and B will come in the middle. Inductive effect, minus I effect will be more prominent here. Okay. Now, these are the other questions. A, B, C, which one is more stable? So CD3. Everywhere plus I. Plus I showing group stabilize the carbocation. Now, everywhere the group is same. So look at the distance factor. Where is plus I factor more prominent? Where the distance is less. Here the distance is less. Right? In the third case, plus I power is more prominent. Right? So 3 will be more stable, followed by 2, followed by 1. Right? Now, this is your alkyl group, this also an alkyl group, this also an alkyl group. All alkyl groups show plus I, right? Now, which alkyl group among all these three will show more plus I? See, this is more branched, more plus I. Comparatively less branched, comparatively least branched. More branches, more plus I. B, followed by C, followed by A. I hope you can solve these sort of questions like this, right? All right. Other carbocations. See. CN, nitro, and alkyl. CN, nitro, and alkyl. CN shows minus I. This shows minus I. This shows plus I. And you know, plus I showing groups, they stabilize the carbocation. So A is maximum stable. Among B and C, more minus I, more withdrawing, least stable. Right? Now, among these two, which one is more stable? A or B? Quickly. Here's a double bond, more S character, more electronegativity, more withdrawing. Means, what does that mean? That means less stability of the carbocation. So B is more stable than A. I hope you can solve these sort of questions like this. Okay. All right. Among A, B, and C, which one is more stable carbocation? Where do you see the more stable carbocation? So CD3, CH3 and CT3. All the three, they show plus I. But where is plus I more prominent? Plus I of CT3 is more, followed by CD3, followed by CH3. So C is maximum, followed by A, followed by B. Plus I groups, more plus I means more stability of carbocation. Simple, right? Now look at this particular scenario. Withdrawing. There is no withdrawing group here, right? So A is maximum stable. Now, fluorine is comparatively less withdrawing than nitro, right? So A, C, then comes your B. This is the stability order. All right, look at these cases. Arrange the following according to their stability order. It's again the similar question, right? Only 1 plus I showing, 2 plus I showing groups, 3 plus I showing groups, more the plus I showing groups, more the stability. So C, B and A, right? Now you can understand it like this. This is the carbocation here, positive charge here, positive charge here. On one side only you are getting the sigma electrons. Here you can say from this side as well as this side you are getting the sigma electrons. Here on two sides you are getting the sigma electrons, right? So sigma electrons, they are going to decrease the positive charge intensity, due to which stability will increase. So B, maximum stable, followed by C, followed by A. CH3 positive, CH2D, CHD2, CD3, right? D has got more plus I than H, right? So more D's, more plus I, more stability. So this is going to be the stability order. Simple. Now nitro, cyanide, fluorine, all are showing minus I. All show minus I. But minus I of nitro is prominent, followed by this, followed by this. So C will be more stable, then B, then A. Right? Okay, guys? All right. Look at these two. Sulfur carrying negative, oxygen carrying negative. This part is same, even this part is same. Now, where is the negative charge more stable? You tell me. Where is the negative charge more stable? Quickly. Sulfur carrying negative, oxygen carrying negative. They belong to same group. In the group, VCD plays a role. More size, less VCD, more stability. Right? This is the stability order. Among these two, this is sp hybridized carbon. This is sp2 hybridized nitrogen. Electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen. More electronegativity, more S character. Right? More S character. More electronegativity. Negative charge is more stable and more electronegative. Negative charge is more stable and more electronegative. So A greater than B. A greater than B. Okay. Now these are anions basically, carbanions. These are carbanions. Now, stability of a carbanion. Stability of a carbanion. Carbanion is stabilized by minus I and destabilized by plus I. So minus I groups, they stabilize the carbanion. Plus I showing groups, they destabilize the carbanion. They destabilize the carbanion. Okay. So this is one simple rule which you have to remember. One simple rule which you have to remember. So tell me the answer of this question. This is carbanion, everywhere there is a negative charge, right? Now CH3, plus I showing. This is minus I, this is minus I. Minus I groups, they stabilize the carbanion. More minus I means more stable carbanion. So C followed by B followed by A, right? NF3, positive, fluorine, CD3. This CD3 is plus I showing. This is minus I showing. This is minus I showing. Minus I of NF3 positive is more than that of fluorine, right? So A is more stable, followed by B, followed by C. Because these are carbanions, right? These are carbanions. These are carbanions. All right. A, B, and C. A, B, and C. Where is the negative charge more stable? Where is the negative charge more stable? Quickly. See, this oxygen is going to withdraw the sigma electrons, right? Here also, it's going to withdraw the sigma electrons. Here there is no oxygen. Here oxygen is closer towards negative charge. So more prominating withdrawing nature. More prominating withdrawing nature, right? Electron withdrawing groups, they stabilize the carbanion. So B is more stable, followed by A, followed by C. So this is the order. This is the order, right? This is the order. Now, among these four, or just leave this aside. Don't introduce it. Look at these three. This part is same everywhere. This part is same everywhere, right? Sulfur carrying negative, oxygen carrying negative. These two, they belong to same group, VCD. VCD is going to be VCD. More size, less VCD, more stability. Sulfur carrying negative, oxygen carrying negative. Which one is more stable? Sulfur carrying negative is more stable than that of oxygen carrying negative. Now, oxygen and nitrogen, they belong to same period. They belong to same period. Electronegativity. Negative charge is more stable on more electronegative. So oxygen is more electronegative than that of nitrogen, right? So negative charge is more stable on oxygen than that of nitrogen. So ABC is the order. Yes? Done? Simple? Okay. Tell me the answer of this question. It's again simple. It is again simple. This will show minus I, even this will show minus I. Minus I of fluorine is prominent than that of iodine, right? And these are carbanions basically. Fluorine carrying negative, iodine carrying negative. They belong to same group, VCD. More size, less VCD, more stability. This is the order. This is the order. Correct? Correct? Now, these are your carboxylic acids, 1, 2, 3. Here you have electron withdrawing, no electron withdrawing. Here it is plus I showing, right? Okay, arrange the following according to their acidic strength. Wait, let me give the rule first of all. Let me give the rule first of all. As I've told you, strength of acid, it is directly proportional to stability of conjugate base. Stability of conjugate base, right? Stability of conjugate base. And conjugate base is stabilized by electron withdrawing groups, minus I groups, right? Inversely proportional to plus I showing. This is the logic. This is the logic. This is the logic. This is the logic, right? Strength of acid is directly proportional to stability of conjugate base, and conjugate base is basically anion. That is stabilized by what? That is stabilized by electron withdrawing, minus I showing. Only this thing you have to remember. If you remember this thing, you are done. You are sorted. See guys. First of all, this is the site from where hydrogen is going to leave. This is the site from where hydrogen is going to leave. This is the site from where hydrogen is going to leave. So take H positive out. Take H positive out, negative charge on oxygen. Take H positive out, negative charge here. Take H positive out, negative charge here. So you made the conjugate base. Now, where is the conjugate base more stable? Electron withdrawing groups, they stabilize the conjugate base. So in the first one, the conjugate base is more stable. So first one is going to be maximum acidic, followed by plus I showing group. They destabilize the conjugate base, right? So C is going to be least acidic, and it's going to be B here. It's going to be B here, right? Now A, B, C, D. Tell me the order of the acidic strength. Tell me the order of the acidic strength quickly, right? This is minus I. This is plus I, right? This is minus I. Nothing here. So what has to be the order? My dear students, be careful in these sort of questions. This is carboxylic acid. This is carboxylic acid. This is phenol. This is OH. This is OH. You have to be careful. This is also OH. Carboxylic acids are stronger than that of phenols, right? Carboxylic acids are stronger acids than that of phenols. So A and B are going to be better acids than that of C and D. It is evident. It's done. No discussion. Now among A and B, where is the acidic strength more? Strength of acid is directly proportional to electron withdrawing, minus I plus I. So A is more acidic, followed by B. Now among C and D, among these phenols, minus I withdrawing. So C will be more acidic than that of D. You have to be careful with this as well. Be careful with this as well. Okay? You have to see first of all whether you are given with phenol, carboxylic acid or what. So short way, you have to remember this strength of acid is directly proportional to electron withdrawing. More electron withdrawing groups, better acid. Okay? All right. Look at this particular scenario. Carboxylic. So this is minus I showing. Here it will show plus I. Here it will show minus I. Right? Acidic strength directly proportional to electron withdrawing. So minus I. Cn is minus I, fluorine is minus I. But Cn has got more prominent minus I. So A is more acidic, followed by C, followed by B. Done. Now among A, B, C, carboxylic, phenol, carboxylic. So A and C will be more acidic than that of B. Whatever B is, leave B aside. B is least acidic. Now among A and C, here fluorine shows minus I. You have got no minus I, right? So C is more acidic than A than B. Clear? C is more acidic than that of A than that of B. I hope it's clear. I hope it's clear, guys. All right. Arrange the following on the basis of their acidic strengths. Now, only one fluorine, 2 electron withdrawing, 3 electron withdrawing. More electron withdrawing, more acidic strength. Right? More electron withdrawing, more acidic strength. As simple as that. Now, among these, OH, phenol, this is carboxylic. Carboxylic is always maximum acidic. No comparison at all. Now, among A and B, this is phenol, NF3 positive, this is fluorine. NF3 positive has got more minus I. More withdrawing. More withdrawing means more acidic strength. So A, then comes your B. Then comes your B. Correct? Then comes your B. All right. 2 more questions and we are done. Among these two, this is the side from where hydrogen is going to leave as H positive. This is the side from where hydrogen is going to leave as H positive. Now carbon number 1, 2 and 3. At carbon number 3 there is fluorine. 1 and 2. At carbon number 2 there is fluorine. So where is withdrawing nature more prominent? In the first one, more acidic. More acidic. Now among these 3, take H positive out, negative charge. 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 Stability of conjugate base. These negative charges are stabilized. Conjugate base is stabilized by more electron withdrawing. Right? This is 3-membered ring. Right? More electronegative. More electronegative. Right? And more electronegative means more electron withdrawing. More electron withdrawing is going to stabilize what? It is going to stabilize the negative charge more. Right? So this is the order of their conjugate basis stability, and this is the order of their acidic strength as well. Yeah? Done? Is it clear? Guys, this is simple, right? I hope this is clear. This ring is more electron withdrawing because of more angle strain, more electron withdrawing. It is going to stabilize the conjugate base more. Simple. I hope it's clear. Okay. This is important. CHF3, CHCl3. Let's make their conjugate bases. Take H positive out, it becomes CF3 negative. Right? Take H positive out, it becomes CCl3 negative. Now, which conjugate base is more stable? What do you think? My dear students, over here carbon is attached with fluorine. Over here carbon is attached with chlorine. In case of fluorine, there are no vacant orbitals. In case of chlorine, there are vacant d orbitals. Vacant d orbitals. If there is a vacant d orbital, there can be back bonding, and back bonding stabilizes the conjugate base. Back bonding stabilizes the conjugate base. So this particular conjugate base is more stable. So this particular acid is going to be stronger. Okay. Now among these, take H positive out, negative charge here. Take H positive out, negative charge here. Oxygen, it does not have any vacant orbital. Sulfur, it has vacant d orbital. So there can be back bonding. Due to back bonding, it stabilizes the conjugate base. More stable the conjugate base, stronger is going to be the acid. So which acid is better strong? Which acid is stronger? This particular acid is strong. Okay, right? One question, the last question, which is your homework, right? You are going to let me know the answer of this particular question in the comments. You have to arrange them on the basis of their basic strength, right? Basic strength. Let me tell you the order first of all. Basic strength, or let me tell you strength of base, right? Is directly proportional to, right? Is directly proportional to electron donating groups, right? And since we are talking about plus I, so it is plus I directly and inversely proportional to minus I. This is the rule which you are going to use, and let me know their answers in the comments afterwards. Okay. So your inductive effect is done and dusted. Perfect. I hope all the things, whatever I have taught you in the today's session, I hope all the things are clear. Right? So do let me know in the comment section if all the things absolutely are clear or not. Perfect. So with this, people, I'm taking a leave. I'll see you with with the chapter solution, since a lot of students are asking for the solution chapter. So I'm planning to do that on the platform, Unacademy platform, through a special class, which is free for everyone, right? And my dear students, the ones who still want to get enrolled into the Avengers 3.0 batch, you guys can still join in, right? The batch link is still open. The batch link is still open. You guys can still join into this particular batch, right? And you exactly know how to do it. We are teaching you in this particular batch, like me, Ambika ma'am, Shreya sir, and HSP sir. Perfect. 75% of this particular batch is in recorded format and 25% is live, right? All the tests, everything is included. Link is there in the description box of the video. You just have to use the code as WASSIM 10, right? This is the code by means of which you will be getting the majority of the discount, right? I believe it's clear to everyone. Since a lot of students have already joined in, the ones who still want to join in, you guys can join in, right? And the access towards this Avenger 3.0 batch is till your NEET examination. But do not forget to use this particular code by means of which you get the majority of the discount, and you are just going to get this course at 8,999, right? If you have any sort of queries related to this particular batch, do let me know in the comment section of this particular video, right? The next session of GOC will be in the upcoming week, not in this week, okay? In the upcoming week. Perfect. I believe all the things are clear, right? Wonderful. So people, with this, I'll be taking a leave. I'll see you in the next session. You guys take care till then. God bless you all and love you all, people.